This topic is called Urban Resilience Assessment Toolkit. Planning tools and practices. The contents of the topic are learning objectives. Urban Resilience Assessment Toolkits, URATs, application of URATs in the planning process. Tools used in the application of URATs. Illustrative case studies. Rotterdam, the Netherlands. Quelimane, Mozambique. Mexico City, Mexico. Singapore. Paris, France. Key takeaways. Learning objectives of this topic are to understand the process of applying Urban Resilience Assessment Toolkits URATs in urban planning and governance. Identify tool used in the application of URATs in urban planning. Learn how toolkit results are linked to action planning, budgeting, and monitoring. As global urbanization accelerates against a backdrop of intensifying climate change and socio-economic volatility, the concept of urban resilience has moved from the periphery of ecological theory to the core of spatial planning. For academic and policy-making audiences, the challenge lies in operationalizing this multifaceted concept, moving beyond bouncing back to a transformative bouncing forward. In academic literature, an Urban Resilience Assessment Toolkit, URAT, is defined as a systematic framework of indicators and methodologies designed to measure an urban system's capacity to withstand, adapt to, and transform in response to disruptions. Rather than a single static tool, URATs are conceptualized as integrated decision support mechanisms that translate abstract resilience theories into measurable spatial and socio-economic variables. Assessment is the prerequisite for effective planning. Current tools are generally categorized by their scale and focus. Holistic Multidimensional Tools. City Resilience Index, CRI, developed by Arup and the Rockefeller Foundation. This tool evaluates 12 goals across 4 dimensions: health and well-being, economy and society, infrastructure and environment, and leadership and strategy. UN Habitat's City Resilience Profiling Tool, CRPT, a comprehensive diagnostic tool that maps the interdependencies between urban elements, e.g., water, energy, and governance, to identify systemic vulnerabilities. Sector-specific tools. Many tools focus on high-impact stressors. For instance, Flood Resilience Measurement for Communities, FRMC, provides specialized indicators for hydrological risks, while newer tools focus on urban heat island, UHI, intensity using spatial land surface temperature data. Bottom-up and community-led tools. Urban Community Resilience Assessment, UCRA, developed by the World Resources Institute, WRI. This focuses on social capital and neighborhood-level vulnerabilities, ensuring that marginalized voices, often omitted in top-down GIS modeling, are included in the resilience profile. In professional practice, applying urban resilience assessment toolkits within a planning framework follows a cyclical, multi-stage process. It is rarely a one-off measurement. Instead, it is integrated into the comprehensive plan or disaster risk management (DRM) strategy of a city. The application generally follows 5 functional stages: scoping and system mapping, data collection and ground truthing, gap analysis and vulnerability profiling, strategy formulation and scenario testing, monitoring, evaluation, and learning, MEL. The first step is scoping and system mapping. Before using a toolkit like the City Resilience Index, CRI, planners must define the system boundaries. This involves identifying critical dependencies. For example, if a city's economy relies on a single port, the toolkit will be calibrated to prioritize maritime and logistical infrastructure. Action. Identifying stakeholders, utilities, emergency services, community leaders. Outcome. A conceptual map of the city's primary assets and potential hazards. The second stage is data collection and ground truthing. This is where technical tools like Kobo Toolbox or GIS are applied. Quantitative data. Planners pull hard data from municipal databases, e.g., age of water pipes, elevation maps, hospital bed capacity. Qualitative data. Field teams use mobile surveys to capture soft resilience factors, such as community trust in local government or the prevalence of informal neighborhood mutual aid groups. Spatial analysis. GIS toolkits overlay hazard maps, e.g., 100-year flood zones, with social vulnerability maps, e.g., areas with high elderly populations. The third state is gap analysis and vulnerability profiling. In this stage, the data is fed into the assessment framework, e.g., the UNDRR scorecard, to produce a resilience profile. Benchmarking. The city is scored across various dimensions, e.g., governance, environment, economy. Identification of single points of failure. The toolkit might reveal that while the city has strong flood walls, engineering resilience, it lacks a redundant power grid, meaning a single station failure could shut down the entire drainage system. The fourth stage is strategy formulation and scenario testing. Planners use the resilience profile to justify budget allocations. Scenario planning. Using tools like Community Viz, planners can simulate the impact of a risk such as 2-meter sea level rise. They can then, virtually, test interventions, such as building a new park, nature-based solution, versus a concrete levee, to see which provides a better resilience ROI. Mainstreaming. Resilience goals are mainstreamed into traditional zoning laws. For instance, the assessment might lead to a new policy requiring all new developments in a specific zone to include on-site water retention. The last stage is monitoring, evaluation, and learning, MEL. It includes using feedback loops to pivot strategies based on performance. Because resilience is adaptive, the assessment must be repeated. The feedback loop. After a minor storm or economic shock, planners rerun the assessment toolkit to see if the implemented strategies actually reduced recovery time. Adaptive management. If the toolkit shows no improvement, the planning strategy is pivoted to address the newly identified weakness. There are specific tools used in the application of URATs in the planning process for data collection, resilience profiling, scenario planning, etc., such as Kobo Toolbox is a suite of tools for data collection that works primarily through the Open Data Kit (ODK) standard. In urban planning, it is defined as a mobile computer-assisted personal interviewing (MCAPI) tool. Planners can collect data in informal settlements or disaster zones without an internet connection. It automatically captures GPS coordinates, allowing field data to be synced directly with GIS software, like QGIS or ArcGIS, for vulnerability mapping. It can record photos of damaged infrastructure, voice recordings of community interviews, and signatures, which are critical for social resilience assessments. Kobo Toolbox is used to bridge the gap between top-down satellite data and bottom-up community reality. Many resilience indicators, e.g., access to clean water, or perceived safety, cannot be measured via satellite. Kobo Toolbox is the tool used to gather this ground truth data through household surveys. Following a shock, e.g., a flood or earthquake, it is used to quickly map the extent of damage to buildings and infrastructure, helping cities manage the response phase of the resilience cycle. Because it supports local languages and can be used by non-experts, volunteers, citizens, it is a key tool for participatory resilience planning, ensuring that marginalized populations are included in the urban data profile. The Disaster Resilience Scorecard for Cities, developed by the United Nations Office for Disaster Risk Reduction, UNDRR, serves as a critical diagnostic tool designed to help local governments monitor and review their progress in implementing the Sendai Framework for Disaster Risk Reduction 2015 to 2030. It is structured around the 10 essentials for making cities resilient, providing a systematic framework of approximately 117 indicators that assess a city's preparedness, response capacity, and recovery potential across multiple dimensions, including governance, infrastructure, and social equity. By utilizing this tool, municipalities can establish a baseline of their current resilience status, identifying chronic resilience deficits and hidden vulnerabilities that often escape traditional planning processes. In the context of urban resilience planning, the application of the scorecard facilitates risk-informed governance by shifting the focus from reactive disaster aid to proactive prevention and capacity building. The process is inherently participatory, typically involving multi-stakeholder workshops that bring together diverse representatives, from government officials to community leaders, to validate data and build local ownership of the results. This collaborative assessment enables planners to prioritize high-risk sectors, realign municipal investments, and integrate disaster risk reduction (DRR) directly into long-term urban master plans and sectoral strategies. Ultimately, the scorecard acts as a decision support tool that bridges the gap between theoretical resilience concepts and the practical application of sustainable urban development. Community Viz is a sophisticated geographic information system (GIS) extension designed to facilitate scenario planning and real-time impact analysis within urban environments. Unlike static mapping tools, Community Viz functions as a spatial spreadsheet, allowing planners to create what-if scenarios by adjusting land use variables and immediately visualizing the consequences through dynamic indicators and 3D modeling. Its primary strength lies in its ability to quantify the trade-offs between different development paths, such as the relationship between increased housing density and its subsequent impact on water consumption, traffic flow, or carbon emissions, making complex urban data accessible to both professionals and the public. In terms of urban resilience, Community Viz is applied to model climate adaptation and disaster preparedness by integrating local vulnerability data with future growth projections. For instance, the software is frequently used in coastal resilience planning to visualize how sea level rise or storm surges might intersect with proposed infrastructure, enabling cities to identify resilience-positive zoning strategies before implementation. By fostering a participatory environment, Community Viz helps build social resilience. Stakeholders can collaboratively explore scenarios in real-time workshops, which reduces conflict and ensures that resilience strategies are grounded in community values and defensible data. Rotterdam in the Netherlands, Quelimane in Mozambique, Mexico City in Mexico, Singapore and Paris in France cases illustrate how cities use urban resilience assessment toolkits to plan for resilience in different contexts. These cases will be briefly presented in the 5-stage framework of application. In Rotterdam, the application of the City Resilience Index, CRI, marked a shift from traditional flood defense to a holistic living with water philosophy. Instead of just building higher walls, Rotterdam used the CRI to assess its vulnerabilities across 4 dimensions: health and well-being, economy and society, infrastructure and environment, and leadership and strategy. Scoping and system mapping. Planners mapped the city's hydrological polder system. They identified that because 90% of the city is below sea level, the urban drainage system, the river delta, and the harbor were inseparable systems. Data collection and ground truthing. The city used advanced 3D hydraulic modeling to map water flow. They ground truth this with social surveys to measure water awareness among citizens, discovering that residents had a false sense of security due to the dikes. Gap analysis and vulnerability profiling. The CRI revealed a major robustness gap. While dikes were strong, the city had no backup for when sewers were overwhelmed by cloudbursts. Strategy formulation and scenario testing. The Sponge City strategy was developed. They tested scenarios where rain intensified by 20%, leading to the creation of water squares, like Bentham Plain, that store water and provide public space. Monitoring, evaluation, and learning. The city tracks the water storage capacity added per square meter of public space and uses resilience officers in every department to ensure new projects meet these standards. Quelimane is a coastal city highly vulnerable to sea level rise, cyclones, and chronic flooding. Before using the toolkit, the city struggled with unplanned urban growth and a lack of data-driven planning. The City RAP tool is designed for small to medium-sized cities with limited data. It follows a bottom-up approach where local government staff, rather than outside consultants, lead the assessment. Scoping and system mapping. The City RAP tool defined the scope as the intersection of coastal mangroves, informal settlements, and colonial-era drainage canals. Data collection and ground truthing. Due to a lack of digital sensors, municipal staff conducted participatory mapping. They walked with residents to mark high water marks on trees and buildings from previous cyclones to map flood zones. Gap analysis and vulnerability profiling. A critical ecosystem gap was identified. The loss of mangroves for firewood was the primary reason the city was losing its natural buffer against storm surges. Strategy formulation and scenario testing. A resilience framework for action, RFA, was formulated. The primary test was comparing gray infrastructure, seawalls, versus green infrastructure, mangrove restoration. Monitoring, evaluation, and learning. Success is measured by the survival rate of mangrove saplings and the reduction in property damage in hotspot areas during subsequent rainy seasons. Mexico City realized that engineering alone, pumping water out, was insufficient. Their CRI assessment led to the CDMX resilience strategy, which restructured municipal governance around 5 pillars. The outcome was creation of a dedicated resilience office in city government that coordinates across previously siloed departments: water, transport, and environment. They transitioned from gray infrastructure to the Parc Lineal Grand Canal, converting an abandoned drainage canal into a green park that reduces heat islands and allows soil to absorb water, mirroring Rotterdam's water squares. In terms of governance, regional coordination was established between the city and the surrounding Mexico basin to manage the aquifer sustainably. Scoping and system mapping. They mapped the social ecological system of the Valley of Mexico. They included the aquifer, the sinking soil, subsidence, and the complex social hierarchy of water access. Data collection and ground truthing, data on seismic vulnerability and water delivery was collected. They ground truthed satellite sinking data by measuring the physical tilt of historic buildings and infrastructure. Gap analysis and vulnerability profiling. A social equity gap was identified. The periphery of the city was most vulnerable to both water scarcity and flooding, despite being the source of much of the city's labor. Strategy formulation and scenario testing. The CDMX resilience strategy was formulated, testing how decentralized water harvesting could reduce pressure on the central aquifer. Monitoring, evaluation, and learning. MEL. They monitor the subsidence rate, how many centimeters the city sinks per year, as a key indicator of whether their new water management policies are working. Singapore is often cited alongside Rotterdam as a leader in resilience governance. Their outcome was the integration of resilience into the Singapore Green Plan 2030 and the creation of the Centre for Livable Cities, CLC, which serves as a knowledge hub to ensure resilience is embedded in every long-term land use plan. They moved from functional drainage to the ABC Waters program, active, beautiful, clean. This turned utilitarian canals into community parks and naturalized rivers, e.g., Bishan Ang Mo Kio Park, similar to Rotterdam's multifunctional dikes. Resilience is a core requirement for all building permits, requiring developers to integrate greening and water-sensitive design. Scoping and system mapping. The scope covered the entire national boundary, treating the island as a closed-loop system for water, energy, and land use. Data collection and ground truthing. They used a digital twin, Virtual Singapore, to collect real-time data from millions of sensors. They ground truth temperature data using Cooling Singapore mobile weather stations. Gap analysis and vulnerability profiling. Resource scarcity gap was identified specifically regarding food and water imports, leading to the 4 National TAPS water strategy. Strategy formulation and scenario testing. They used the Long-Term Plan Review, LTPR, to test scenarios for 2100, including a 1 meter sea level rise and a 3 degrees Celsius temperature increase. Monitoring, evaluation, and learning. MEL. They use strict key performance indicators, KPIs, embedded in building codes. For example, every new development must replace 100% of the greenery lost during construction. Paris used the resilience framework to address urban heat islands and social isolation, leading to a major shift in municipal zoning. The city appointed a chief resilience officer to ensure that climate adaptation is a priority in the city's budget, specifically targeting vulnerable neighborhoods identified during the CRE assessment. Scoping and system mapping. They defined the system as the Urban Heat Island, UHI. They mapped the relationship between high-density stone buildings, lack of parks, and public health data from heat waves. Data collection and ground truthing, thermal imaging data across the city was collected. They ground truthed this by placing sensors in schoolyards before and after they were unpaved to see the actual temperature difference. Gap analysis and vulnerability profiling. A cooling access gap was identified. Many residents lived more than a 10-minute walk from a cool island, green space, or water. Strategy formulation and scenario testing. The Oasis Project and the 15-minute city were formulated. They tested how opening schoolyards to the public during weekends could provide a resilience network. Monitoring, evaluation, and learning. MEL. Paris monitors the temperature differential between Oasis schoolyards and traditional asphalt streets, aiming for a 2 to 5 degrees Celsius reduction. Key takeaways from this topic are as follows. A common failure in early urban planning was treating resilience as a standalone environmental issue. Success requires cross-departmental integration. Resilience should be a filter through which every municipal project, from new roads to school renovations, must pass, rather than a separate budget line. Multifunctional design provides a fail-safe, rather than safe-fail, system. planners should prioritize nature-based solutions because they grow stronger over time, whereas concrete only degrades. There is often a gap between what a satellite sees and what a resident feels. Ground truthing is essential. Data is only useful if it is validated by the people it affects. Without community buy-in, resilience infrastructure is often neglected or even vandalized. Methods such as citizen science and participatory mapping should be used to supplement GIS data. This ensures the community feels ownership of the resilience strategy. Generally, the hardest hit areas are rarely the ones with the most expensive infrastructure, they are the ones with the least social capital. Resilience requires social equity. Social vulnerability indices should be used during the gap analysis phase to prioritize investments in underserved neighborhoods first. The most successful cities stopped viewing resilience as a disaster expense and started viewing it as value creation. Co-benefits attract funding. When formulating a strategy, the co-benefits, e.g., this park reduces heat and lowers local healthcare costs, should always be quantified to secure diverse funding streams.